Good morning, everyone. I'm Sherry Ann Sacharias, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. Today, I will be discussing on the second part of digital modulation techniques. This is a topic that comes under Module 4 in the course Digital Communication. The topics of this presentation are as follows. We will start with an introduction to what is quadrature phase shift keying. Then we will derive an expression for the error probability of Qpsk. Finally, we will look into the generation and detection of a coherent Qpsk signal. Now we will start with a quick review on what is coherent phase shift keying. Coherent phase shift keying is a modulation technique in which the phase of a sinusoidal carrier is changing in accordance with the signal to be transmitted. So why is it called coherent? It is called coherent because at the receiver you have a phase recovery circuit that ensures that the locally generated carrier at the receiver is synchronized in both frequency and phase to the carrier used at the transmitter side. So coherent phase shift keying techniques are of two types. You have binary phase shift keying and quadrature phase shift keying. In binary phase shift keying, there are only two symbols to be transmitted, and the phase of the carrier can take one of two values, either 0 or 180 degree. Now, in quadrature phase shift keying, there are four symbols that can be transmitted, and the phase of the carrier can take one of four values. For example, 45 degree, 135 degree, 225 degree, and 315 degree. In this lecture, we will be focusing on quadri-phase shift key. Quadrature phase shift keying is a modulation technique in which four symbols can be transmitted. So this is a kind of memory signaling scheme in which two information bits are grouped to form a symbol. So the symbols that can be transmitted are 10, 00, 01 and 11. So we have already studied in the first part of the fourth module that the advantage of an memory signaling scheme over a binary signaling scheme is that the transmission bandwidth is reduced because the bandwidth is inversely proportional to n times the bit duration. So because of the fact that there are four symbols that can be transmitted, the phase of the carrier in the case of quadrature phase shift keying can take one of four equally spaced values such as pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. Another feature is that the carrier frequency Fc is chosen to be equal to Nc by Tb. This ensures that each transmitted bit contains an integral number of cycles of the carrier. So in Qpsk, the transmitted signal is defined as Si of t is equal to root of 2e by t cos 2 pi fct plus 2I minus 1 into pi by 4. So the signal is defined for a duration 0 to capital T, where capital T is the symbol duration. E represents the transmitted signal energy per symbol. Fc is the frequency of the carrier, and the phase of the carrier changes according to the symbol transmitted. So I takes values 1, 2, 3 and 4. So corresponding to the symbol transmitted, the phase of the carrier changes as pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. Now we look at the signal space diagram or constellation of Qpsk. So in order to obtain the signal space diagram, we need to represent the transmitted signal Si of t as points in an n-dimensional space. These points are known as message points. So for that, we first need to find the basis function corresponding to the transmitted signal. So we know that in Qpsk, the transmitted signal is defined as Si of t is equal to root 2 e by t cos of 2 pi fct plus 2I minus 1 into pi by 4. So by applying the trigonometric formula for cos of a plus b, we can simplify this expression as SI of t is equal to root of 2e by t cos of 2i minus 1 pi by 4 into cos 2 pi fct minus root 2e by t sine of 2i minus 1 pi by 4 into sine 2 pi fct. So we are using the formula cos of a plus b is cos a cos b minus sine a sine b. So from this expression, you can see that the transmitted signal can be expressed as a linear combination of two basis functions. So you need to define the basis functions phi1 of t and phi2 of t. So the basis functions should be defined in such a way that they must be orthonormal in nature. That is, two conditions have to be satisfied. One is each basis function must be normalized to have unit energy. That is, integral 0 to t, phi1 square of t and phi2 square of t must be equal to 1. The second condition is that the basis functions must be orthogonal with respect to each other. That is, integral 0 to t phi1 of t into phi2 of t dt must be equal to 0. So we can define the basis functions which satisfy these two conditions for the signal SI of t as phi1 of t is equal to root of 2 by t cos 2 pi f ct, and phi2 of t is defined as root 2 by t sine of 2 pi f ct. So once we obtain the basis functions, the next step is we need to find the signal vector. The signal vector or the projections of the signal on the basis function. So we know that any signal SI of t finite energy can be written in terms of its basis functions as, if there are two basis functions, you can write it as SI1 phi1 of t plus SI2 phi2 of t, where SI1 represents the projection of the transmitted signal on the first basis function and SI2 represents the projection of the transmitted signal on the second basis function. So if phi1 of t is defined as root 2 by t cos 2 pi fct, then from this you can see that SI1 can be defined as root e cos of 2i minus 1 into pi by 4. That is the remaining term. Similarly, if phi2 of t is defined as root 2 by t sine 2 pi fct, then you can define SI2 as minus root e sine of 2i minus 1 into pi by 4. So the signal vector associated with the four message points can be defined as SI is equal to SI1, SI2, where SI1 is the projection of the ith symbol on the first basis function and SI2 is the projection of the ith signal on the second basis function. So from the previous slide, we can see that SI1 is equal to root E cos of 2i minus 1 pi by 4 and SI2 is equal to minus root E sine of 2i minus 1 into pi by 4, where I takes values 1, 2, 3, 4 corresponding to the four symbols that can be transmitted. So this shows the four symbols that can be transmitted using Qpsk 10, 0, 0, 0, 1 and 1, 1. So when you substitute I is equal to 1, you will get the projections of the first signal on the first basis function and the projections of the first signal on the second basis function. Okay, similarly, if you substitute I is equal to 2, you will get the projections of the second signal on the first basis function and the projection of the second signal on the second basis function. Okay, so this is actually giving you the coordinates of the message point. The signal vector actually gives you the coordinates of the message point. So corresponding to I is equal to 1. Okay, so that is corresponding to the first symbol. Suppose 1, 0 is the first symbol. Okay, so corresponding to that first symbol, the coordinates of the message point are, when you substitute I is equal to 1, you will get root E cos of 2 minus 1, that is cos of pi by 4. So root E into cos pi by 4 is root E by root 2. So that is plus root E by 2. Okay, now corresponding to I is equal to 1, if you want to find the projection of the signal on the second basis function, it would be minus root E sine of 2 minus 1, that is sine of pi by 4, that is minus root E by 2. So that is what you get here, minus root E by 2. So this is the coordinate of the message point corresponding to the first symbol. Similarly, If I want to find the coordinates of the message point corresponding to the second symbol, I have to substitute I is equal to 2. So when I substitute I is equal to 2, you will get the coordinates of the message point corresponding to the second symbol as root e cos of 2 into 2, 4 minus 1 cos 3 by 4, and this would be minus root e sine of 3 by 4. So you will get it as minus root e by 2 and minus root e by 2. Okay, so like this you have to calculate the coordinates of the message point for the four symbols. So once you calculate the coordinates of the four message points, we will plot this on an n-dimensional space. So here what is the value of n? The value of n is equal to 2 because you have two basis functions. So the value of capital N will be equal to 2. This figure over here shows the signal space diagram of QPSK. So you can see that there are two basis functions, phi1 and phi2. Since capital N is equal to 2, so the QPSK signal is two-dimensional because of the fact that there are two basis functions. At the same time, there are four symbols that can be transmitted. So you have four message points corresponding to the four symbols that can be transmitted. So if you look at the first symbol that can be transmitted 1, 0, the coordinates of the message point are plus root e by 2 minus root e by 2. So corresponding to 1, 0, the coordinates are plus root e by 2 minus root e by 2. So this is the message point corresponding to the symbol 1, 0. Okay. So here plus root e by 2 is the projection of the symbol on the first basis function, and minus root e by 2 is the projection of the signal on the second basis function. Similarly, if you consider the next symbol 0, 0. So corresponding to the next symbol 0, 0, the coordinates of the message point are minus root e by 2 minus root e by 2. So you can see the coordinates minus root e by 2 minus root e by 2. So this is the message point M3 corresponding to 0, 0. Okay, so this is the message point corresponding to 0, 0. Similarly, the message point corresponding to 0, 1 is minus root e by 2 plus root e by 2. Minus root e by 2 plus root e by 2. So this is the message point 0, 1. The message point 1, 1 can be seen as plus root e by 2 plus root e by 2. So this is the message point corresponding to the symbol 1, 1. Okay, so we will get 4 points corresponding to the 4 symbols that can be transmitted. So once you get the 4 points, then the next step is, once you find the signal space diagram, the next step is I need to divide it into a number of decision regions. Here, based on the number of transmitted symbols, I will divide it into the M decision regions. So since M is equal to 4, the signal space I have to divide it into 4 regions. So in order to divide it into 4, what I'm going to do is I'm going to form a square joining the 4 points, and then I'm going to draw the perpendicular bisectors through the sides. Okay, so I'm going to draw the perpendicular bisectors through the sides of the square that is formed by joining the 4 message points. That is how I will divide it into 4 decision regions: Z1, Z2, Z3 and Z4. This figure shows the sequences and waveforms involved in the generation of a QPSK signal. So consider an input binary sequence 01101000. So this input binary sequence is first divided into two: an odd numbered sequence and an even numbered sequence. So the odd numbered sequence is 0, 1, 1, 0, and the even numbered sequence is 1, 0, 0, 0. So once you divide it into two sequences, this waveform corresponds to the QPSK component SI1 phi1 of t, and this waveform corresponds to the QPSK component SI2 phi2 of t. So when you add these two waveforms, you will get the QPSK signal S of t, because the QPSK signal S of t is defined as SI1 phi1 of t plus SI2 phi2 of t. So when you add these two waveforms, you will get the QPSK signal. Now, if you closely look at this waveform, you can see that this waveform is actually the binary PSK waveform corresponding to the sequence 0110. So you can see that 0 is represented by a sinusoidal wave and 1 is represented by a sinusoidal wave with a phase shift of 180 degree. Similarly, the next 0 is represented by a sinusoidal wave which again has a phase shift of 180 degree. Now, similarly, if you look at this sequence over here, even this waveform corresponds to a binary phase shift keying waveform that corresponds to the sequence 1000. So 1 is represented by a sinusoidal wave, 0 is represented by a wave with a phase shift of 180 degree. So you can say that your coherent QPSK system is equivalent to two coherent BPSK systems working in parallel, which uses two carriers phi1 of t and phi2 of t, which are in phase quadrature. That is, the carriers are separated by 90 degree. Now, once we have obtained the signal space diagram of QPSK and divided it into M decision regions, now we can derive the probability of error for QPSK systems. So, in a coherent QPSK system, we know that the received signal can be defined in terms of the transmitted signal as x of t is equal to Si of t plus W of t, where Si of t is the transmitted signal and W of t is a sample of additive-white Gaussian noise. So here I takes values 1, 2, 3, 4 depending upon the symbol that is transmitted. Now, when the received signal is given to a detector, which is a bank of n product integrators, the output of the detector would be the observation vector. This observation vector represents the projections of the received signal on each basis function. So here, in the case of a QPSK system, the observation vector has two elements because of the fact that your QPSK signal has two basis functions. Okay, so your observation vector will always have n elements. Here, n is equal to 2. So the observation vector has two elements, x1 and x2, and you can define x1 as the projection of the received signal on the first basis function. So you can define x1 as x1 is equal to integral 0 to t x of t into phi1 of t dt. So this can also be written in terms of the transmitted signal as Si1 plus W1, where Si1 is the projection of the ith signal on the first basis function and W1 is your noise component. So now we already know what is the projection of the ith symbol on the first basis function. So that is equivalent to root E cos of 2i minus 1 pi by 4 plus W1. Now this term cos 2i minus 1 pi by 4, this takes values either plus 1 by root 2 or minus 1 by root 2 when I is equal to 1, 2, 3 or 4. So you can simplify this as x1 is equal to plus or minus root of e by 2 plus w1. So similarly, the second element of the observation vector is the projection of the received signal on the second basis function, and it is defined as x2 is equal to integral 0 to t x of t into phi2 of t dt. That is can be written in terms of the transmitted signal as Si2 plus W2, where W2 is the noise component and Si2 is the projection of the transmitted signal on the second basis function. So that we have already seen in the previous slides, it is equal to minus root E cos of 2i minus 1 pi by 4. So this takes values either plus 1 by root 2 or minus 1 by root 2. So you can simplify it as x2 is equal to minus plus root e by 2 plus w2. So you can see that both x1 and x2, the elements of the observation vector, are independent Gaussian random variables having a mean of Sij and a variance of n naught by 2. So here Sij is either Si1 is plus or minus root e by 2 and Si2 is minus plus root e by 2 and the variance is n naught by 2. N0 by 2 corresponds to the power spectral density of white Gaussian noise. So the decision rule is being made in such a way that suppose the observation vector or the received signal point falls inside a region Z1, the receiver decides that S1 of t was transmitted. So when will this decision go wrong? This decision will go wrong suppose if it is given that S1 of t is transmitted. But noise is affecting the received signal in such a way that the received signal point falls outside the region Z1. So if the received signal point falls outside the region Z1, the receiver will take a wrong decision. So now we will find the probability of error in such a case. So we know that a coherent QPSK system is equivalent to two coherent binary PSK systems working in parallel. So one is known as the in-phase channel and the other is known as the quadrature channel. So they use carriers which are in phase quadrature or separated by 90 degrees. So X1 represents the in-phase channel output and X2 is the quadrature channel output of a QPSK system. So these are viewed as the individual outputs of coherent binary PSK systems. And we know that capital E represents the signal energy per symbol. So since two bits are grouped together to form a symbol, the signal energy per bit is E by 2 and the noise spectral density we know that it is N0 by 2. So since the QPSK system is equivalent to two binary PSK systems, the average probability of bit error in each channel of the QPSK system is equal to the average probability of bit error in a BPSK system, that is equal to P dash is equal to 1 by 2 error function complementary of root EB by N naught, where we know that EB is the signal energy per bit is E by 2. So that is you will get P dash is equal to 1 by 2 error function complementary of root E by 2 N naught. Now the bit errors in the in-phase and quadrature channels of the QPSK system are independent, which means that if I want to calculate the average probability of correct decision, the average probability of correct decision would be 1 minus the probability of error. So the probability of correct decision is 1 minus P dash, that is in a single channel. So if I want to calculate the average probability of correct decision due to the combined action of the two channels, since the two channels are independent, if two events are independent, probability of A and B is probability of A into probability of B. So here the probability of a correct decision would be 1 minus P dash into 1 minus P dash. That is 1 minus P dash the whole square. Now on substituting P dash, we get the probability of correct decision as PC is equal to 1 minus 1 by 2 error function complementary of root E by 2 N naught the whole square. So this you can expand this. So you will get 1 minus error function complementary of root E by 2 N naught plus 1 by 4 error function complementary square of root E by 2 N naught. Now, if you know the probability of correct decision, the average probability of symbol error for a coherent QPSK system is probability of error would be 1 minus the probability of correct decision. So if you take 1 minus PC, this 1 gets cancelled and you will get error function complementary of root E by 2 N naught minus 1 by 4 error function complementary square of root E by 2 N naught. Now, as this ratio E by 2 N naught is much greater than 1. So, if this E by 2 N naught ratio is much greater than 1, an important property of your complementary error function is that as x increases, error function complementary of x decreases. So, if E by 2 N naught is much greater than 1, this term over here becomes a very small value which can be ignored, and finally we will get the probability of symbol error or bit error rate for a QPSK system is equal to the error function complementary of root E by 2 N naught, where E stands for the transmitted signal energy per symbol and N naught by 2 is the power spectral density of white noise. Another method of deriving the average probability of error in a QPSK system is using the signal space diagram. So if you look at the signal space diagram of QPSK, there are four message points which are circularly symmetric with respect to the origin. So in that case, the probability of error can also be defined from the signal space diagram as PE will always be less than or equal to 1 by 2 summation over k error function complementary of dik by 2 into root n naught, where dik is the distance between the transmitted signal points or message points. So suppose M1 is the transmitted message point. So if M1 is the transmitted message point, M2 and M4 are the points which are closest to M1. So if E by N naught is very large, you can eliminate the contribution of the most distant point M3. This is because your message point M1 is 1 1. The message point M3 is 0 0. So the likelihood that both the bits will go into error will be very small. So that is why you can eliminate the contribution of the most distant bit, and you can consider dik as the distance of the message 2 from 1 and the distance of the message M4 from M1. So this probability of error can be calculated as PE will be less than or equal to 1 by 2 error function complementary of D12, which is the distance between the message points 1 and 2, by 2 root n naught plus error function complementary of d14 divided by 2 root n naught. Here d14 is the distance between the message points m1 and m4. So the Euclidean distance between the points m1, m2, or the points m1 and m4, they will be the same. It will be equal to root e by 2 plus root e by 2, which is equal to root 2 into e. Okay, so substituting this value over here, we will get the probability of error as 1 by 2 error function complementary of root EB by N naught, where EB is related to the signal energy per symbol as E is equal to 2 times EB. Okay, so this is the average probability of symbol error or the bit error rate of a QPSK system. So if you look at this, you can say that the coherent QPSK system achieves the same average probability of bit error as that of the BPSK system, but it uses only half the channel bandwidth. So that is the advantage of the QPSK system over the binary phase shift keying system. And another advantage is that for the same bandwidth, channel bandwidth, your QPSK system can transmit information at twice the bit rate when you compare it to your BPSK system. Now we will look into the generation and detection of coherent QPSK. So this is the block diagram of a typical QPSK transmitter. The incoming binary data sequence is first transformed into a polar form using a non-return to zero level encoder. So the symbols 1 and 0 is being transformed into a binary wave amplitude plus root EB and minus root EB. This is then given to a demultiplexer. The demultiplexer is used to divide the binary wave into two separate waves consisting of the odd and even numbered input bits, that is represented by the signals A1 of t and A2 of t. The two binary waves A1 of t and A2 of t, they are then used to modulate a pair of quadrature carriers or orthonormal basis functions. So A1 of t is being multiplied with phi1 of t and A2 of t is being multiplied with phi2 of t. So the result is you will get a pair of binary PSK signals. These binary PSK signals can be detected independently because of the fact that phi1 of t and phi2 of t are orthogonal to each other, and this pair of the PSK signals are then added to form the QPSK signal. So this is the block diagram of the Qpsk receiver. The Qpsk receiver consists of a pair of correlators or product integrators which have a common input. The input is the received signal. Each correlator is supplied with a locally generated pair of coherent reference signals phi1 of t and phi2 of t. The correlator outputs are x1 and x2, which are the individual elements of the observation vector. So this output correlator output x1 would be the projection of the received signal on phi1 of t, and x2 would be the projection of the received signal on phi2 of t. This is then given to a decision device. So x1 is given to a decision device which is being compared with a threshold of 0. So if x1 is greater than 0, the receiver takes a decision that 1 is transmitted. If x1 is less than 0, you take a decision that 0 is transmitted. Similarly, the output of correlator 2, x2, is also given to a decision device where you are comparing it with a threshold. So if x2 is greater than 0, receiver takes a decision that 1 is transmitted. If x2 is less than 0, you take a decision that 0 is transmitted. And this binary sequences at the in-phase channel and the quadrature channel output is then combined in a multiplexer in order to reproduce or give an estimate of the transmitted binary sequence. So the last topic is the power spectra of Qpsk signal. So if you look at the in-phase and quadrature components of a Qpsk signal, depending upon the symbol transmitted in the signaling interval minus 3b to plus tb, both the in-phase and quadrature components will either equal plus g of t or minus g of t, where g of t is the symbol shaping function, which is defined as root e by t for the interval 0 to t. Okay, so from this you can find the power spectral density as the power spectral density would be the energy spectral density divided by the bit duration, and the energy spectral density is found by taking the squared magnitude of the signal's Fourier transform. So you will find that both the in-phase and quadrature components, they have a common power spectral density of E sinc square of TF. So this is found in the same procedure as you did it for BPSK signals. So we know that for a QPSK system, both the in-phase and quadrature components are statistically independent. Hence, the power spectral density of QPSK signal equals the sum of the individual power spectral densities of the in-phase and quadrature components. So you can write SB of F is equal to 2E sinc square of TF. Since E is equal to 2 EB and T is equal to 2 TB, you can write this as 4 EB sinc square of 2 TBF. So this shows the power spectral density of a QPSK signal. Thus we conclude this lecture. We have started with the basic concept of quadrature phase shift keying. Then we have discussed how to plot the signal space diagram and how to derive the probability of symbol error for QPSK. We also looked into the generation and detection of a QPSK signal and the power spectral density. Thank you.